So as we continue on from key geologic principles, we're going to go next into relative and absolute age dating. And you have a good sense about what relative age dating is already, and that's all that people could do for the first 150 years, 200 years maybe in geology. And so people collected fossils and they recognized that there are different fossils in different layers. And so they put together this geologic timescale. The thing is, of course, is they didn't have any understanding about the absolute age of the Earth. And so it took a little bit more time in order to develop that. But people developed schemes about how they could figure out exactly how they could do that. And so we're going to go into that a little bit, but not in great detail. That's for historical geology. But for here, you can see Ray Troll's version of, traveling the fossil highway, his geologic time scale, and he shows you the various fossils that you find in every interval here. And so it's kind of important that way. You won't have to memorize this, okay? So and when I was a student, we had to memorize this, okay? But it was a 5-hour course back then. So now it's only a 4-hour course. So yeah, here it is. This is the geologic time scale. And what it is, the rocks that comprise each one of those time periods, they're called systems actually. Each one of those systems can be mapped on the surface of the Earth as well. And so what you see here is a version of the mapping. And so this is all of North America. And the rocks in the very far north up there, that's called the Canadian Shield. We're going to get into that when we talk about plate tectonics, but that's the Canadian Shield, and there's all these various hues of red, orange, so almost, well, they're not quite purple there, so they reserve purple for sedimentary rocks here. But you can see all of the various colors on this map. It's a very colorful map. That is essentially looking at a geologic timescale on the surface in map view, okay? So those are Precambrian Age rocks. Remember we talked a little bit about Archean and Proterozoic? Well, that's the reds and the pinks up there, and we'll talk a little bit more about it later on in this session here. Sedimentary rocks wrap around that. Now, those rocks were actually, the sedimentary rocks were removed by erosion by glaciers actually over the northern part of North America here. But around the perimeter, you get these sedimentary rock successions. So you see the greens, the yellows, the light yellows, the blues, the sort of aqua blue, and then the purple, the light purple, and so forth. Those are all sedimentary rock successions of various ages. Whenever you see the reds on here, those are usually igneous rocks of some sort. And so, but anyway, they were mapped based on their lateral continuity and their faunal succession and their superposition, right? And so the younger rocks overlie the older rocks, and it just became this puzzle that people put together. And this was, of course, known pretty well back in the late 1800s by, when they did the last explorations of the West. In fact, there was a geologist, you probably know him, his name was John Wesley Powell. And he took a group of men down the Colorado River to study the geology down there and to explore it as well, right? So that was the story of John Wesley Powell back in the 1870s, 1869, I think he went on that excursion. So anyway, what I'm going to do now is to give you a short excursion also, looking at some rocks, principally actually in the West, and so, but also some locally here as well. So in this next slide, I'm going to show you, these are Lower Cambrian sandstones. So these actually accumulated on the edge of the North American continent in eastern Nevada, as it turns out. California didn't exist back then. And so in eastern Nevada, you're pretty much at the continental margin, and these sandstones were deposited off the weathering of the igneous and metamorphic rocks. Well, this is above that unconformity we call the Great Unconformity, but this is a rock unit called the Prospect Mountain Quartzite right here. Very dense rock. It's been very deeply buried, but at the same time, it's really a sandstone, but it's so dense, in fact, that when you break it, it breaks along planes of weakness. It doesn't have, of course, quartz sand doesn't have any cleavage in it, but it breaks along fractures and things like that. And so it's a very, very dense rock, I guess you could say. But overlying that, and you don't get it too much in this area right here where where it's been carved out by a glacier. But if you went farther south along the Snake Range, you would see rocks that are younger than that, rocks that overlay that quartzite, the Prospect Mountain quartzite. And here they are actually laid out for you in a mountain range that's just to the east, well, a couple of mountain ranges to the east of the Snake Range. And this is called the Wawa Mountains here. And this is in western Utah here. We were in eastern Nevada. Here we're in western Utah. And this is one of the highways that stretches across, very lonely highway that's a different succession of rocks here, in fact. So these are mostly carbonates. There's a handful of shales in here as well, where you can see where there's kind of like notches along the horizon there. But in the far distance, in fact, you can see the valley beyond there, and the Snake Range would rise in the distance and be snow-covered usually. But this is, well, Eye of Needle is down at the bottom here. You get the whole bunch of other different rocks here. But you get over 10,000 feet of them, in fact, which is absolutely amazing. So this is a Cambrian succession of carbonates, which in fact would have accumulated in a place a lot like the Bahamas, right? And so that's the sort of setting that we envision when we look at carbonates like limestones and so forth, right? In this case, all of these limestones and shales, in fact, were deposited on the western margin of North America at that time, before California existed. 10,000 feet of it, though, enormously thick succession here. What do you find in those rocks? Well, you find trilobites. When I was out here, I was looking for brachiopods, actually, and so I would dissolve those carbonates, and you would get out phosphatic brachiopods out of the succession here. So really kind of cool. And that's what geologists do. We go out and we explore places, and it's already been mapped, so we go out and we do stratigraphy. We collect fossils. We try to understand what the time period was like, right? So these are what we call Cambrian Age Rocks. So if it was lower Cambrian over in the Snake Mountains, this is the middle and upper Cambrian here. And so I'm still working on these rocks, actually. After all these years, I still work on these things. And I take students out into the field. Graduate students go out into Utah with me sometimes and get to work on some of these rocks. Here's some rocks that are local, though. These are, and I work on local rocks too, but these are rocks that are exposed in a quarry, again, it's pretty near, it's Compton Ridge in that area. I don't know if you're familiar with Branson, but Compton Ridge, there's a big quarry there. And there's a highway that cuts by this. In fact, this is on one side of a fault. It's called the 10 o'clock run fault. And here you see a whole succession of lower Ordovician. Those would be younger than the rocks that we just looked at in Utah. And then at the very top, there's an unconformity. In fact, not the very top of this photo, but at the top of one of the ledges here. And I think, let me get my idea. Okay, yeah, there's a little yellow line that cuts across there. And that's the base of the Mississippian, actually, above that. And so in southern Missouri, as it turns out, we're missing part of the succession here, where, it's been cut out by erosion. It's been removed by erosion, let me put it that way. It was gently uplifted, and then those rocks were eroded away. Other rocks may have been deposited over the top, but they too were eroded away. And then we're left with this disconformity here. So this disconformity, you recall that word, right? That's where sedimentary rocks over other sedimentary rocks. And you have no indication of a break there, except there's missing faunal zones. Well, what's missing here? It's the upper Ordovician, the Silurian, and the Devonian. All three of those are missing, right? And then you get the Mississippian deposited over the top of that. And so that's the Compton limestone, that little limestone that runs across in the middle part of that image. And then at the very top where it's sort of like reddish in color, that's also Mississippian in age. And that actually belongs to a rock unit we call the Osagian around here, the Osagian series. And so that's the Pearson limestone, named for Pearson Creek, just east of Springfield. So the relative ages here are they're not out of order, but they're old rocks at the bottom and younger rocks, of course, on top of that disconformity, which cut out some of the rocks. And then even younger at the very top, we get into the middle part of the Mississippian here. Same age rocks, actually, that crop out around Pearson Creek over on the east side of town. That is a relative age succession right there, even though we have a disconformity in the middle of it. And it's one in which we try to understand, well, why did that unconformity form? Well, there had to have been some sort of event that lifted the rocks up and removed the intervening rocks. through erosion. And so that episode is very poorly known, in fact, but it was part of the Ozark uplift, the uplift of the Ozark Plateau. And then on the next slide, these rocks are all dipping. Now, we're going to talk about structure later on in here, but these are all dipping. So the youngest rocks in this case are actually on the left-hand side, and the older rocks are on the right-hand side. It's a place called Dinosaur Ridge. Well, guess what? These are even younger than the rocks that are at Branson. So if we had lower division or lower Cambrian first, and then we had middle and upper Cambrian, then we had lower division, then an unconformity, right? That's in Missouri, those last bits there, but here we're in Colorado. And if you're in Colorado and driving around Denver along I-70 and you head up into the mountains, you drive right through here. And in fact, you'll see a little walkway on one of the benches over there. And that's called Dinosaur Ridge right here. Why do you suspect? Well, you know why. They find dinosaurs in these age rocks. And so what you see here is they call it the Morrison Formation over on the right-hand side there. It's a series of gray shale and some sandstone, and you get a little bit of red shale in there as well. But they find dinosaur fossils in there. They find dinosaur footprints in the sandstone. And so it's a place that would have been dry land at one time. Up above that, however, it goes into another rock unit that's part of the Upper Cretaceous. And so we're missing a fair amount of the Jurassic here. We're missing the lower part of the Cretaceous, and then all of a sudden you get into the Upper Cretaceous at the top. And those are actually, it includes some marine rocks, in fact. And so there were marine waters that once covered the middle of Colorado. If you want to learn more about that, take my historical geology class, but it's really a fascinating story about how there were once swimming reptiles that were out in the middle of western Kansas and like eastern Colorado, swimming across a feature that ran all the way from the Arctic Ocean down to the Gulf of Mexico. It was salt water that went through there. They call it the Western Interior Seaway. But those are Cretaceous age rocks at the top up there. And how do we know? Well, because they have younger fossils in them than what's down in the Jurassic down here in the Morrison Formation. And so you find different kind of fossil assemblages as well. So it's not just one person going out and collecting fossils. Generations of geologists have gone out. Generations of paleontologists have gone out and discovered these things before. And so that's this idea of putting together a geologic timescale. Again, we still don't know what the absolute age dates are yet until the 1950s. And in the 1950s, somebody came along who cracked the code and figured out how to get the absolute age dates out of this. And so we'll go on to him next. Well, real soon here anyway. It's just the difference between what's absolute and what's relative. Relative means that it's like a stack of papers. You don't know when that last stack of paper was placed down. You only know that the paper that's at the top is the youngest and the paper at the bottom is the oldest. It doesn't tell you that one of them was placed there on Tuesday and the last one was placed on Friday of last week. So that's a relative age dating scheme. So when people tried to figure out exactly how old the Earth was, they didn't know how to do it exactly. So they tried to come up with schemes that would enable them to figure it out. So people thought, well, you know, if fossils have evolved and we have different fossils in different layers, then maybe there's such a thing as an evolutionary rate at which things can change. And of course, that's total hogwash. That's not true. There's not an evolutionary rate that we can use as a time scale. And so, but it was Lyell who proposed that, and it's like, and of course he was wrong. And he had suggested, in fact, that it's 80 million years for the entirety of the Cenozoic. Now, the Cenozoic, as you recall, is modern life. That's the stuff that happened after the non-avian dinosaurs went extinct. And in fact, it's not that far off, but in fact, it's wrong still. It's 66 million years instead of 80. Other people thought that, you know, well, if you've got these big, thick successions of sedimentary rock around the world, and you could maybe make an estimate about what rates they accumulated at in modern settings, maybe you could apply that to the ancient record. And they did that. And of course, they were wrong. And so people tried different sort of strategies then. It was Edmund Halley, the guy who named Halley's Comet, right? Well, they named Halley's Comet after him, Edmund Halley, Sir Edmund Halley. He said that, well, the rivers are slightly saline and the oceans are enormously salty, as we know, 34.5 parts per thousand of salt, halite, right? Or at least it's the ions that make up halite, so chlorine and sodium. And so he said, if we know the salinity of a river and we know the salinity of the ocean, we can figure out how long it took to develop that salinity. He was thinking that the oceans would become more and more saline through time. And it was John Joly who actually calculated a value of 90 million years based on the salinity of the rivers. And so he was actually not only wrong, but wrong-headed with this. So Sir Edmund Halley was actually incorrect in thinking that the oceans would get saltier and saltier. As it turns out, the oceans have been the same roughly since Cambrian time. They've had the same salinity. That's because we have plate tectonics operating, and what happens is that many of the salts actually get scrubbed out because the ocean basins will be replaced. As it turns out, the water too gets scrubbed of many of these ions in places in the deep oceans, in ocean trenches and things like that. And so that's an incorrect sort of statement. It was William Thomson. He became known as Lord Kelvin. And Sir William Thomson, he said that, well, if the Earth was once totally molten, and then we take the rate at which, like if you're a blacksmith, let's say, and you took a cast iron ball of iron, right? And we know that the center of the Earth is iron, right? And if it's super hot today, and they suspected it was even then, right? You had to have some sort of heat source for all the volcanoes, right? And so they said if it's a black body radiation is what they called it. So you heat up a chunk of iron red hot until it's glowing white almost, right? So the color of the sun almost yellow and white. And then it slowly cools and becomes light orange and then darker orange and then red. And eventually it goes to a black body if it's an iron ball. And so they call that black body radiation. From the calculations of what the surface temperature of the Earth is, he back calculated and said, well, the Earth must be 24 to 40 million years. And of course, that's way off, of course, right? He didn't know about radioactivity. And radioactivity, in fact, is what generates most of the heat in the Earth. It's not that cooling that is giving off heat from the core. It's actually the inclusion of radioactive elements both in the mantle and the core, and that material gives off heat. And so we have heat that's still being generated today. I don't know if you can't call it new heat because the material is down there, but it's radioactivity and the decay of radioactive particles that's giving off that heat. It was Henri Becquerel who came up with that idea. Henri Becquerel and also Madame Curie, right? So Madame Curie had studied radium and she learned about radiation as well. It took her life, in fact, but she was one of the earliest women scientists who contributed to this grand scheme of trying to figure out how the Earth works. Henri Becquerel did as well. He used a cathode ray tube and he shot, it wasn't electrons, but it was particles at an electrode essentially. And so he got things to jump across there. And so he saw that there's substances, in fact, that were radioactive. Along came Claire Patterson. So Claire Patterson is the guy in the photograph here. You probably have never heard of him before, but he's actually a scientific hero. For a couple of reasons, actually. He thought, well, if we take things like granite, there are certain minerals in granite that will include uranium, and we can actually measure the decay rate of uranium then to figure out what the age of things are. And he tried that on meteorites first, and he came up with 4.54 billion years old, and then actually 4.56 billion years old. And he says, well, we should be able to do that with old rocks from the granites on Earth as well. And so he took the granites, and of course, as it turns out, there was too much lead in his samples. So Claire Patterson is like, where's this lead? Oh, and then he realized there's atmospheric lead on the planet Earth right now. It comes from the gasoline. Now, I don't know, when you go to fill up your car, have you ever wondered, why do they call it unleaded? It's because they used to put lead in gasoline. They put an additive in gasoline that would cause it, because the they call them, well, the valves at the very top of an engine. There's intake valves and exhaust valves. And to keep those valves from being lubricated, to keep them lubricated, they introduced lead into the gasoline. Well, what they didn't know at the time was that lead was poisonous, especially in the form that was being produced by the gasoline fumes. They used to put lead in paint too, if you're familiar with that. Paint used to chip off of rooms, interior rooms, and children would eat the lead paint. They looked like potato chips. They didn't taste quite as good. Oh, yeah, I probably ate a couple of myself. Yeah, they didn't. They're not salty, right? So you don't eat paint chips, especially ones that had leaded paint. And so many of the old houses, even in Springfield here, have leaded paint in them from the 1960s, 1950s, some of the older houses. So lead was everywhere on Earth back in the 1950s when he was doing his studies. And so he built the first clean lab. And then, of course, he would scrub his samples to get all the lead off. And he built a lab which was essentially isolated from atmospheric lead poisoning, essentially. And he testified before Congress in the 1970s, early 1970s or late 1960s. And in Congress, he says, yeah, this is horrible. And they had doctors and other people that came in. He's one of the guys that gave us the Clean Air Act. And his testimony was used to help develop the Clean Air Act of 1971. Actually, it was President Nixon who signed that into law. And then after that, we got the Clean Rivers Act of, I think it was 1972 or 73. And actually, Nixon had signed both of those. It was the biggest environmental advance forward that we'd ever made in this country. You have to put yourself back in the 1970s now. And I lived through this. I didn't live at the place where this happened, but in Cleveland, one of the rivers in Cleveland caught on fire. Let that sink in a little bit. How can you have a river catch on fire? It's because it was so polluted with volatiles and gasoline and diesel fuel and things like that. Well, it's not that way anymore. That's because of the Clean Water Act of 1972, I think it was. They cleaned up the environment in the early 1970s. We had our first Earth Day in 1970. He gave his testimony about this time, and everybody was concerned about pollution because they knew it was harming children and the development of children. Their brains were not functioning properly under the influence of lead. That's one of the side effects of lead poisoning, is having brain damage. So you would think that, they'd want to clean the stuff up. Well, in the 1970s, they mandated it so every single car had to begin burning unleaded fuel. But that meant they kept the leaded fuel around for a few more years for all the cars that had to have it. Otherwise, their engines would be destroyed in 10, 20,000 miles because the valves weren't being lubricated. But unleaded, you don't have to worry about that. So they began to make a harder alloy for valves to burn unleaded gas. And then they also put in a catalytic converter at that time into automobiles. All because of this guy. We took the lead out of the gasoline. We put catalytic converters on cars, and pollution had dropped like, it's 1/30 of what, 30% of what it used to be out of an automobile. Just imagine that. If you imagine an automobile, let's say it's not even a good and well-tuned up car, right? And it drives down the street and it leaves a cloud behind. Think about that times 3, okay? That's what it was like back in the 1960s. I recall that. This guy made that possible, and his name is Claire Patterson. Claire Patterson. So he was born in 1922, died and passed away in 1995, but he made the biggest contribution to humanity as we know it from an environmental standpoint, and then also because he was able to date rocks for the first time accurately with absolute age dating. They'd tried it before with rubidium strontium and a few other sort of chemical systems, but he used uranium-lead, uranium-238, and lead-207. That's the system that he got to work properly. And he went back and he dated some of the meteorites. And in the meteorites, he found that the meteorites were the same age as what we think the interior of the Earth is. And that's 4.56 billion years old. Now, okay, speaking of meteorites, this is a meteorite down at the bottom. Now, this is not the one that he dated, but this is one. If you look at that, you can see the green crystals in there. That green crystals in there, those are olivine, essentially like olivine anyway. And so there are some sort of unusual minerals like perovskite and a few other things that may be in there as well. And then it's surrounded by nickel and iron. And when you mix nickel and iron, it makes a certain mineral. So camosite and taenite are the name of the minerals in that. But this is a special type of meteorite. They only find a handful of these every year, maybe. I don't know if they even find them every year, but there's a handful of these, and they're very valuable because what they represent is they are right at the core mantle boundary of some ancient asteroid. When that asteroid broke apart and pieces of that asteroid come to Earth and give us a light show at night when they collide with Earth, and they're called pallasites. And so these things actually record what's in another planet, what was at the core of another planet. And so we have three different kinds, general kinds of meteorites. Stony meteorites would be like the mantle of Earth. The stony iron meteorites, which are like this, which is like a core mantle boundary. And then there are iron nickel meteorites, so ones that would represent the core of that other planet that had been destroyed at one time. Well, what happened to it? It was right next to Jupiter. And in fact, today we recognize it as the asteroid belt. Well, the asteroid belt has a few large asteroids, but a lot of small ones. And as it turns out, they like to run into one another because there's so many of them. So it's a lot like bumper cars out in the asteroid belt, busting off other pieces, and then eventually they can put them into an orbit around the Earth, and eventually the Earth sweeps them up. And so this is a pallasite down here. They're very famous pallasites are found around the world, but that's one of them right here. Just a beautiful sample right there. So that is a stony iron meteorite right there. And so Claire Patterson comes along, and other people began to study this stuff as well. Well, they had been for a long time, and they realized that the one mineral that seems to be better than any other mineral, now they used to have large samples in order to date things. Now you just need a single crystal to date things, and it's this mineral right here. Now that's zircon right here. Zircon is zirconium silicate. Now this is going to look familiar to you. ZrSiO4. Do you remember what mineral had the SiO4 radical attached to it, that silicate mineral? It was olivine. Zircon is a lot like olivine. Well, what do you know about olivine? Well, olivine is pretty hard. It's like a hardness of 7.5 or 8. And then this has a hardness of 7.5. It's very heavy, so it's easy to separate, okay, from the lighter minerals. You crush it down to sand grain size, and then you have a table that sifts these things essentially for you. You can even pan these things like you're panning gold. It's pretty heavy, right? It has a specific gravity, 4.6. It crystallizes at a very high temperature, just like olivine as well, except it only occurs in the more felsic varieties. It occurs in felsic and intermediate varieties, let me put it that way. So zircon is that mineral right there. And so what they do now, they can actually train a laser on it, and they can get a series of ages across, and they can actually record the cooling history of that zircon. Because it crystallizes first out of a magma like olivine, it records the original uranium that was in that magma. And so when it does that, of course, that uranium eventually is going to decay to lead. So you take lead-238 and you take the ratio of all the other sort of components that may be in there, but especially lead-207, I think it's 207, and you weigh the two, and it's like, how many of these atoms do I have? How many of these? Well, you can do that with a mass spectrometer. Mass spectrometer is an instrument by which you can do what we call isotope geochronology. So the whole study of absolute age dating has its own name. It's called chronology. You're studying time, actually. You're not studying the age of the rocks. You're studying the age of crystallization of components of that rock. So the zircon's really important for that. So in the chart, yeah, that's the periodic table. Over here I got zirconium, circle there. Zirconium is the element Zircon is the mineral that's made out of zirconium. So that's the ZrSiO4 there. So it has a lot in common with olivine as well. So it's important. It's an important mineral. In fact, I would say it's the most important mineral that crystallizes out of a magma. So almost every granite, almost every volcanic ash that is either felsic or intermediate has zircon in it. And so you can date them. And so that's really important. So people have been doing this for the last 30 years. That's the primary thing that isotope geochronologists do, is they go out and they find zircons. Well, as it turns out, you can find them in a lot of different places. You can even find them in a sandstone, right? Because that granite is going to weather and decay. But as it turns out, the zircon doesn't decay like an olivine crystal might and doesn't turn to clay. It stays robust. And so it's just as tough as quartz in the sedimentary environment. So they get kind of a minimum age on the sedimentary history then that way. So let me tell you a little bit about uranium-lead dating now. Now, radioactivity is pretty wild. And you guys already know about isotopes, right? You know that there are certain isotopes that we call them stable isotopes. They're not radioactive. Yet you also know that there are certain isotopes that are radioactive, like carbon-14, right? Well, we can age date carbon-14. It has what we call a half-life of about 5,260 years. And so by knowing the quantity of carbon-14 in a sample, we can then determine its age compared to the other carbon that may be in it. So we can do the same thing, in fact, with uranium. So we take that zircon, we measure the amount of uranium-238 in it. It's lead-206 at the end, by the way, not 207. 207 is still radioactive, by the way. So the 206 at the end is not, however. So lead-206 is not radioactive. You can see here in this diagram, now it's a little difficult to show you, so I'm going to show you, and I think I've got another example. Yeah, on the next slide here, I'll show you what this chart looks like up close. It's a little different from this one. But what happens in uranium in decay, in radioactive decay, is that there are different varieties of it. There's alpha decay, beta decay, and gamma rays that are given off. And so alpha decay is where you take essentially a helium neutron. Remember that helium had two neutrons, helium nucleus. It has two protons and two neutrons in it. A helium nucleus has two protons, two neutrons in it. That particle shoots out of uranium-238. When that occurs, you've lowered the atomic number by 2. You've lowered the atomic mass by 4, because there are 4 particles, right? When we count the atomic number, we're only worried about the protons, however. And so you lose 2 protons, 2 neutrons in one spontaneous decay, one alpha decay. The next decay is a little bit trickier, because that's where we can have a neutron that decays into a proton. Now, that can occur, yeah. So what happens is that electron goes away. What makes a proton? If you mix a proton and an electron together, it neutralizes it, right? So one's negative and one's positive, right? And then it has a neutral charge when you put that electron in there. Well, if you spontaneously spin off an electron, it's going to change a proton into a neutron. What does that do to it? Well, it doesn't reduce the weight at all, because it's just one particle that flips a switch, and all of a sudden you've got an extra proton in there. Well, that makes it a different element then, because it's the number of protons that determines what an element is. That's the atomic number. And so the atomic mass stays the same, but the number drops by 1. And so, or it adds 1 to the atomic number, right? So it goes from a neutron to a proton. And so that's the second type of decay. The third type of decay is really where it's just an energy state that goes from high energy to low energy, all of a sudden. And that's called a gamma radiation sort of emission out of these rocks. Most of the time, we're interested in just the alpha and beta decays. And so that's what you see in this. It's a little like a pachinko machine where they release a ball and it goes through all the nails and makes its way eventually down to one of the slots at the very bottom down there. People place bets on things like that, right? This is uranium-238 at the very upper right. You have a decay, an alpha decay there that takes it down to thorium. And then you have a beta decay which increases the number. And I can't see actually the, here, let me see if I can get my slides up a little bit closer here where I can read it. Yeah, it goes to, I think it's, oh yeah, Palladium, I don't remember the name of that element. But then it has another beta decay, and of course you've added now 2 back to the number, and now you have uranium-234. You've reduced the mass by 4, but you've kept, so uranium-238 goes to thorium, to this palladium, I can't remember what it's called, but it's not palladium, I know that. So it's uranium after that, and then it goes into a series of alpha decays, and so that's to thorium, and I can't really make it looks like radon there. Actually radium and then radon, and then polonium, and then lead. Actually, you get down to lead at the end of this at 214. So that's the 214 PB is lead-214. Lead-214 then begins to decay, and it has different pathways that it can take. So it can either have a beta decay, and then it can have an alpha decay after that and go to, it looks like, I forget, tantalum, I think it is. Tantalum over on the left-hand side, so 210, I think it is. But you have a series of these alpha and beta decays, and eventually you get down there to the very bottom. And notice they put the radioactive element U-238 in red because it's radioactive. And then you can see that lead down here, lead-206, is in blue, which means it's not reactive, right? So it's not radioactive. And so here is our decay series. They call that the decay series. Now it takes 4.5 million years for half of the uranium-238 to decay to the lead. So it's going to take 9 billion years. So it's 4.47 down here at the very bottom gives you that number, 4.47 billion years for half of a decay. So if you found the oldest rock on Earth, which is not even, it's not 4.47 as it turns out. If you took the oldest felsic rock anyway, it's 4.03 billion years. It still has more than half of its original uranium in it. And so the rest is going to lead. In fact, it's not radioactive anymore. So that is how these decay caves series work, decaying from one to another. Now, how does it decay? This is a little odd tidbit, but I need to put it out there for you. It's not exactly a clock, but if you can imagine, if you had 100 pennies in your hand and you threw them up in the air and they all landed, you're going to get 49 one time. You'll get 40 sometime, and sometimes you get 60. So there's and you do it enough times, right? So you keep doing it. You keep throwing 100 pennies up into the air, and you count how many are heads, how many are tails. And on average, you're going to get 50 heads and 50 tails, but you have to average it. Any individual decay is not going to be there. But there's so many atoms. So when these things decay, it's not a 1-to-1 ratio, just because, like, half of them decay over 4.5 billion years. It takes a long time for just one of them, one atom, to decay down to that lead-207, because each one of these, in fact, has their own half-life. And so there may be some in here that are like 3 million years, or they could be, 1.5 billion years. I don't remember what all the different decays are in between in these steps, but they all have a certain rate at which they decay. But that's the way it works. And so we don't say that it's like a clock. It's not like a metronome ticking off radioactive decays. It's more like a stochastic process. In other words, it's more like throwing pennies up and getting an average. So that is uranium-238 series right here. Now this is the same diagram, except it's different in the sense that they give you the mass on the x-axis on the bottom down here, and then they give you the atomic number at the top. So instead of going from top and then zigzagging down this way, it's going to zigzag a different way. And so that's uranium-238 up here at the top, thorium, and then the Pa, whatever that symbol is there. I think it's polonium or something. I don't remember exactly. But uranium and then thorium and then radium and then radon, polonium. Actinium, I think, is 218 right there, and then it goes into the lead. So you see polonium and lead all the way through here, and tantalum is the one down here at the very bottom. And so that is the decay series in a different way. So they're showing you a different vector and showing you the decays in a different way down here on the lower right-hand side. And so beta decays go up because the number goes up, right? And then the mass goes down towards the lower left down here. And so uranium goes through these series of decays. It's stochastic. You get what they call daughter products, in fact. That's an important term. I actually use that in exams very commonly. So you have the uranium-238, and then you get a whole series of decay products. At the very end of it, the last decay product, the end daughter product, is lead-206. So lead-206 down here at the bottom. Now, having said this, this is one series right here that people can measure. There are other series as well. People use like strontium is another decay that you can actually get meaningful data out of. So you can get strontium 89, 87, I think it is. And then you can also get strontium. You can get argon decay. So there's actually a radioactive version of argon. You can get lead itself has radioactive isotopes, and those can decay. And they use that in modern sediments, in fact. So I think it's lead 209, maybe go to 207 in 20 years or so. So this is the idea. So the idea of a half-life is pretty important as well. So if we're measuring how much of the uranium is left and how much of the lead is present in a rock, in a zircon crystal, that's going to tell us how far along the decay process it's going, because we know that the standard is 4.47 billion years in order to go to half. As it turns out, so if you go one half-life, that means half of it is decayed. We start with what we call a parent product, which would be the uranium-238. So the parent is uranium-238. The decay product would be called the daughter product. Half of it's gone in one half-life. If half of it's gone in one half-life, how much is gone in two half-lives? Well, it still continues to decay, and another half will be gone in the second half-life. Now, you can't do that with uranium-238 because we haven't even been through the first half-life for it yet. But some of these other ones where you go through decay products, where you want to measure those, like you could measure the thorium in here and see how much lead-206 you have. So thorium-230 to lead-206. You can measure that ratio. And so the first half-life, half of it's going to be gone. In the second half-life, you have only a quarter of the original material left. And after 3 half-lives, you would have 1/8 of the material left. You get the idea. After 4 half-lives, you'd have 1/16. So it's like halving it each time over each interval that is a half-life. So in the first half-life, you miss half. In the second half-life, you're down to a quarter. The third, you're down to 1/8. The fourth, you're down to a 1/16. And then a 32nd, 64, and so forth, right? So that's how half-lives work. It's pretty important. That's a test question right there. So that's how many half-lives does it take to get down to 1/8 of the original parent material? So that's going to be a question I can almost guarantee you. Or something like that. If you had 4 half-lives, how much is left? Well, it'll be 1/16 then, right? You get the idea. So it's 1/2 squared, and then 2 to the third, and 2 to the fourth, and so forth. Okay. Now, with all of this behind us now, many meteorites actually give us an age of 4.46, okay, in billions of years. Moon rocks range from 3.3 to 4.6. Now, the oldest Earth material that we've ever been able to date is a zircon crystal, but it's a zircon crystal that was incorporated into a conglomerate. And so it dates back 4.4 billion years, and it's only one zircon that's dated. There's only a few of them that date back that old, so around 4.48 billion years old. It's in Australia. It's, and I'll show you a picture of it. But it's a place that has, so in other words, to have that zircon incorporated into that conglomerate, it first had to have crystallized in a magma chamber. That magma chamber had to be uplifted and then eroded and accumulate in a conglomerate. And then that conglomerate actually was metamorphosed slightly and then uplifted again. And so that's the one tiny grain is 4.4 billion years old on Earth. So why doesn't it go back to 4.56? If the oldest moon rocks are pretty close to that, 3.3 to 4.6. In fact, the moon rocks also have meteorites there. The meteorites have struck the moon, as you're probably well aware of, right? You can see the craters on the moon. By all rights, Earth should look like that, right? But it doesn't. So the oldest rock that we know of on Earth, a rock now we're talking about that's been dated, it's been dated actually with a different series. It's samarium neodymium, and that dates back to 4.28 billion years. So why do these ages not go back to 4.56? That's what I've been telling you all along, is the age of the Earth. It's because of the origin of the moon. As it turns out, the moon is actually made out of the same stuff that Earth is made out of. And there was a collision early in the formation of the Earth that caused everything to blow up. It was a Mars-sized impactor that hit the Earth. This is the origin of the moon hypothesis. But the same material that's on Earth is on the moon. Roughly 4 billion years ago. It was a little bit older than 4 billion. Let's see, 4.4, I think, was roughly what the age is they give for the origin of the moon. And so, boom, you have this huge impact, and it jettisons a whole bunch of material, which eventually becomes the moon. And it gives us a larger Earth than what we otherwise would have had. And so the moon didn't exist before that. The old hypothesis was that the Earth captured the moon, but we got the largest moon of any of the planets in the solar system. So it makes sense to have had an impact and then send the Earth material orbiting the Earth as part of the moon. And so these radiometric ages are pretty important. So just going to show you a few pictures now. That's called the Jack Hills over here, the photograph on the upper left-hand side. On the right-hand side, you can see the Jack Hills metaconglomerate over here. So it's a metamorphosed conglomerate. It's from that conglomerate, where you see that hammer right there, somewhere within this rock unit. They took a piece of that, they crushed that rock down to smithereens, little tiny sand grain sizes, and they extracted a zircon grain on essentially what is a gold sieve sort of feature. It's like they call them Wolfley tables. They have water running across, and the heavier grains get shunted out towards the end and the lighter grains fall down. It's like panning gold. And so they recovered the zircons because they're heavier, and they took those zircons and then they shoot a laser at them. They ablate the crystal, and then they can measure from the gas that's given off in that plasma. In a mass spectrometer, you can determine the amount of uranium and the amount of lead in it. So if the oldest rocks on Earth are not 4.56, this is the oldest material right there. It's a detrital zircon from that metaconglomerate up here. Now I'm going to show you pictures of these other two too. So there's also the Acasta gneiss. That used to be the oldest known rock on Earth at 4.03. And in fact, not having rocks older than that makes a lot of sense if we did have this impact that created the moon. And then lastly, in this greenstone belt, now this is where you had to use the samarium neodymium, but that's in Quebec. They measured the age from the samarium neodymium as 4.28 in that one. So here's the Acasta gneiss. This is going to take a little bit of background here. Gneiss is going to be one of the rocks that we look at when we talk about metamorphic rocks. So that's next on the list here. But I had to tell you about the absolute age dates first. They found a chunk of granite in a gneiss that was more or less protected from all the metamorphism that was going on. And in the core of that granite, it's called a granite protolith. It's part of that gneiss, but at the same time, it was protected by all the forces that were affecting the gneiss around it. In that, they found a zircon, and that zircon was dated by a guy named Sam Bowering. He's passed away now, but he used to be at MIT. In his mass spectrometer, it's an IGCP-MS is what they call it. In that mass spectrometer, he was able to determine the age is 4.03 billion years old. And so this is up in the north of Canada here. This is also in the north of Canada, but this is a mafic rock. It's ancient sea crust that was smushed between two microcontinents. And what it left behind was this fossil seafloor, essentially, that they were able to date. Now, the trouble with this is, and with samarium neodymium geochronology, is that they don't get precise ages of the age of crystallization. What they get instead is what they call a mantle separation age. You recall when we talked about the zone of partial melting in the Earth? Oh, that's going to be next. So we'll get to that. But that's going to be with plate tectonics. But there is a zone of partial melting inside of the Earth within the mantle, and that's where many of these magmas get generated. Well, that magma that caused this body of rock right here to separate, and then it crystallized. When it separated, part of it crystallized when it separated, or kept that same sort of like samarium and neodymium content in it. When it made its way to ocean floor, as pillow basalts and dikes and all sorts of things that you get, sills and things like that in an ancient ocean floor. And it incorporated the samarium neodymium into it. And 4.28 billion years was the age of that one. So, okay, to summarize, there are a lot of different systems that we can use to get absolute age dates. Absolute age dates vary from relative age dates in the fact that they're calculated in a different way. They're calculated in labs around the world, really. And but it's the relative age dates that were really important in putting the story of Earth together for the sedimentary rock successions anyway, and looking at unconformities, cross-cutting relationships, superposition, things like that. But then when people began to look at the sedimentary record and look where there are volcanic ash deposits, or look where there are intrusives, they can begin to then bracket the ages of some of those time units. And that's where the numbers came from on the geologic time scale. People focus in as like, well, what's at the base of the Cambrian? And so they begin looking for, well, in volcanic ashes. In a volcanic ash, you're going to get some zircons. Those zircons are going to yield an age. What age did they yield? They yielded 542 million years old for that. 542 million years for the base of the Cambrian. So that is how you go about doing the absolute age dates. But there are different kinds of systems that people use. So we've talked about uranium-lead. So really we're talking about uranium-238, lead-206 there. Uranium-thorium is another one. So thorium-230 has a half-life of 75,000 years. So it's good back to about 500,000 years in order to date things. We can use lead-lead as well in order to date things, because remember there are several lead daughter products, and you can eventually take those back to lead-206. And then lead-210 here, that's the one I was talking about with you earlier. I've been a part of collecting samples off the coast of California when I was with the U.S. Geological Survey. We would drop cores into the ocean floor and pull out the sediments, and in the sediments themselves, they record how much lead 210 there is in there, and there's a 22.3 half-year half-life for the lead-210. And so you can measure young ages with that, right? So ages that will go back maybe 150 or 200 years before people were driving automobiles, let's put it that way. And then potassium argon is another system that people have used. They use that because potassium has a half-life of 1.26 billion years. Argon, they use that on muscovite predominantly. In muscovite, you can actually tell the age of fault movements with the micas then. So they use argon-argon for that, an argon-argon system. Rubidium Strontium is an old version that was used. Strontium is used in marine carbonates. Samarium neodymium, like we just talked about, gives you mantle separation ages. Carbon-14 you're familiar with. I gave you the wrong date earlier. I said 5260, but it's actually 5730 is the half-life for that, but it's good for 50,000 years. I, as a geologist who studies carbonate rocks, have actually sent samples off to be carbon-14 dated. As it turns out, they were about 1,200 years old, actually about 1,000 years old and 800 years old. So 800 to 1,000 years old from carbon-14 age dates. It's pretty interesting. It tells us about an uplift age as well. Thermoluminescence is a new one. It was used in archaeology at first, but now it's used for a lot of other things. And so when people find minerals, especially quartz that has been buried, there will be inclusions of beryllium and chlorine in the structure of quartz very commonly, and you can actually get the last time that quartz grain was exposed to sunlight from it. So it has to be a buried sample that you recover, but you can actually tell ages from that. So relatively recent ages, I would say. Apatite fission tract dating is really important as well. They do that in some labs where apatite, remember, is an igneous mineral, and you can get uplift ages from that. And so they go to known elevations. I knew some guys in Antarctica who would climb to the top of mountains just to collect a granite sample there because of the apatite that was contained within it. And that apatite actually records the tracks of cosmic rays that go through it and the density of cosmic rays that go through it. And knowing where it actually occurs, you can date the uplift of when that mountain got to where it is. It's an unusual technique, but it's still fascinating how people come up with these things. There are other systems that people do as well, so you can actually get the magnetic signature out of a rock and try to apply it to what they call the apparent polar wander path. It's a magnetic sort of signature. So remember, we talked about how continents have rotated and moved around, of course, in plate tectonics. And so north is not always where it seems to be. And also, many of the magnetic grains in the sedimentary rocks. It's really important. It's another way, another technique by which people can date ancient sedimentary rocks. Oxygen isotope dating can be used as well. And then lastly, you probably knew about this one, but maybe you didn't. I don't know. Like in the Southwest, right? So there are the ancient Hopi peoples that lived in that area. They used to call them Anasazi, but it's the native tribes that lived in that area back thousands of years ago. Well, they built hogans and they built adobe structures, right? So Pueblo Indians, for instance, right? Well, they made these houses out of wood, and so they can date the dendrochronology of the logs to figure out exactly when it occurred. It's like when you can do some archaeological dating, in fact, so you can get the age of different sort of encampments and things like that. That's the story of relative and absolute age dating. And it's used exclusively in geology and archaeology, and it's pretty important. So even marine sciences do this as well. So absolute age dating, relative age dating, both of them are important. But the really cool thing is, and if you recall the geologic timescale, there were all these layers in there, right? As it turns out, the ages that turned up for each one of those boundaries was consistent. It's not, it's like at the very top, you don't expect to find 500 until you get to the bottom, down to the base of the Cambrian, right? So the 542, for instance, right? Or in the 500 range, you're going to be in Cambrian Age Rocks. You don't find those age dates up in the Cretaceous. You don't find those age dates in the Permian. You don't find them for sure in the Cenozoic, and for sure in any of those. Only in the Cambrian, right? So you're going to get 542 to 488, I think, for the Cambrian. So if you get an isotopic age date of that, you know what age it is. There's so much power in having two systems that merge so perfectly together, so the absolute and the relative age dates merge to give us a very robust understanding about the age of the Earth. Okay, that's it for now. And we'll talk next about metamorphic rocks and After Metamorphic Rocks, we'll talk a little bit, let's see, I forget what's next on the list, but Metamorphic next. So that'll complete our survey of different kinds of rocks in geology, because we've already talked about igneous rocks and now sedimentary rocks. Next, Metamorphic Rocks. Thanks a lot. Talk to you soon. Bye now.